Okay, the last thing for this unit, which I actually should have done a while ago, but I guess I'm doing it now, is something called approximations and Reimann sums. I'm not gonna explain like the limits that you do with it, just because to be honest, I don't really understand that myself. You can look up things online for it. That's how I prepared for the final, was I looked up something online and kind of tried to learn it right before, and it was enough for me. But you can look it up online if you have a question about limits or whatever. I think I'll put a link on the website to the website I used. But I'm talking about, they're called Reimann sums, and Reimann was the guy who basically figured out how to do this. And let's say we have a line like this, and let's pretend like I haven't taught you the definite integral yet. So you just have a line like this, and you want to approximate the area underneath from like here to here. So there are four types of approximation techniques that people use. One, and you're going to see that they're very geometric, and this doesn't take any calculus at all. This takes literally you just drawing things out. So the first one's called a left sum, and what this is you're going to put in a lot of rectangles in between here to basically get an approximation of the area using rectangles. And you're going to be, your width of the rectangles is going to depend on the problem. The problem is going to tell you n equals something, and that's going to be how many rectangles you want to have, or it could be how thick the rectangles are. The problem will tell you. But in this case, let's say n equals 4. So you're going to use 4 rectangles to find the left sum. What we're going to do is we're going to have rectangles where the top left corner of the rectangle is touching the line. So I'll split this into 4 just to make this right. The first one's going to be 0 because the left part of this is a 0, but the second part, you draw it up. The left part's going to touch the line, like that. The second one, it's actually the third one, and then that. So that right there would be the left sum because the left part of the rectangle is touching the line. As you can see, this is an under approximation of what the line is because there's a lot of area that isn't being calculated for that is underneath the line. The next one you may have guessed is going to be a right sum. And depending on the problem, one might be more accurate than the other. It really depends on concavity, which is something we talked about in previous units. But actually, not concavity. I'm sorry. We did talk about that in the last couple of units. But it has to do with if something is increasing or decreasing. As you see, this function is increasing, and my phone just went off. Sorry about that. This function is increasing, so the left sum is going to be an under approximation, while the right sum is going to be an over approximation. So let me draw out the right sum real quickly. That would be like this, where the right part of the rectangle is touching the line, so it's going to look like that. As you can see, this is a huge over approximation because there's all this extra area that isn't actually a part of the line. Okay, the third one is called the midpoint sum, and this is going to be kind of similar to the ones we just did, except instead of being on the left or right, it's going to be in the middle of the rectangle. This one, in my opinion, is probably the hardest one to calculate just because you have to basically know what the heights are going to be in the middle of the rectangle, which involves a lot of halves and stuff. Basically, it'd be like if this is our 4 little barrier things, we would say, oh, what is the height in the middle? The height in the middle is like right there, so the rectangle will look like that. Height, which is in the middle, is like right there, so like that, and like that. So it's going to look like something like that. Now, as you can see, this kind of is more accurate than the left sum or the right sum in many cases because it is an over approximation here, but then an under approximation here, over, under. So depending on the situation, they might cancel each other out and end up giving you a more precise answer. It won't be exactly right 99% of the time. But yeah, it'll give you a much closer approximation because it's doing an over exaggeration, but then it's canceling out with another under exaggeration. I'm just going to redraw this. And so on and so forth. Well, the last one I want to talk about, which is going to be by far the most accurate out of all of them. Oh, wait. I hope you can see this. Most accurate of all of them is something called the trapezoidal sum. The trapezoidal sum, similar to what you think it would be, is going to be using trapezoids. Now, do you remember the equation of a trapezoid? If you don't, this is what it is. It's going to be the distance, well, in the trapezoid, if this is what a trapezoid looks like, this is the height. Oh, I'm sorry, what am I talking about? Oh my gosh. This is the height. This is base 1 and base 2. Then it's h over 2, base 1 plus base 2. And through calculus, you'll probably memorize this really quickly because you'll need to be using it a lot for a short period of this unit. I have this fear that you guys like can't see this. I hope you guys can, because I don't want to re-record these. But so what you're going to do is you're basically just going to take what is the point at the beginning and the end, and you're going to connect them like that. And the first one's going to be a triangle because it starts at 0, but this next one is going to be like here and here, and you're just going to connect a straight line in between and do that. Now, as you can see, this still is not super, like, the exact answer. The exact answer will be using definite integrals, which I talked about a few videos ago, even though I should have taught you this first. But so basically what you would do is you would do the distance in x here. So let's say that this is at 4, so this would be at 1, 2, and 3. It would be 1 because the distance is 1. Divide that by 2. And then multiply this height by, or multiply it by the sum of these two heights. So this is 0, and this is maybe 1, I don't know. That was supposed to be like a tick marker than 1, but okay. So it would be 0 plus 1, and you would get 1/2. So the area, this is 1/2. But then you would have to add all 4 of these together, and that's how you get your approximations. So those are Riemann sums, and use those to approximate what the area underneath a line will be using left sums, right sums, midpoint sums, or trapezoidal sums.